Hello everyone, my name is Edgar de los Santos. I am part of the technical support team here at MIDAS. Today we're going to have a session regarding the soil structure interaction in bridges. What soil structure interaction is, the types of analyses that are related to it, the modeling functions that we have available in the program, and also we're going to see how we're going to apply those modeling functions, and then we can check some of the results that are available in MIDAS. After that, we're gonna go over the design features in the program. First of all, I would like to introduce you to what MIDAS is, and then we're gonna go over the substructure part. MIDAS is an all-in-one solution. It's a structural analysis program that can handle any type of bridges. You can go from the very simple slab bridge to the most complex suspension cable stayed bridge out there. You can also handle any type of analysis in the program. You can do any type of analysis is available. As you can see here, you can go from static, you can perform nonlinear dynamic analysis, and you can also do the design of the entire bridge. So it's an all-in-one solution for bridge analysis and design. Let me just go over what soil structure interaction is. So for those of you who do not know or are not familiar with what soil structure interaction, this is the phenomenon in which the response of soil and movement of the structure influence each other. So let's say when an external force such as an earthquake acts on the system, neither the structural displacement nor the ground displacement are independent of each other. So one influences the behavior of the other. The study of this behavior is what soil structure interaction is. In soil structure interaction is the way in which the soil interacts with the structure itself. As you know, every structure has a load transfer system to the ground. That amount of load that is transferred depends on the location of the foundation, the flexibility of the foundation, and the soil behavior on which the structure is supported on. So the study of this combination is very important so that you can have an idea of what the behavior of the entire structure will be with the simulation of the soil properties in it. You can get displacements, moments, load distribution, and see what the behavior of the entire structure will be. Regarding the types of analysis, there are two methods of analyzing the soil structure or of performing the soil structure interaction. One is the substructure method and the other one is the direct method. The substructure method is based on superposition of events, so it separates the problem into two parts. Free field analysis, in which the response of the soil, the reactions are obtained. This is where the structure, where the structure will be. Those reactions from the soil are taken. The other part is the structure analysis portion. Here the soil is modeled with dampers, spring dampers, and then from there you design the structure with the idealization of the soil properties. This is a more practical method for structural engineers. We don't have to go into much of details of the soil properties, since it's just an easier way of performing the analysis considering the soil. You also have the direct method, in which the soil structure system, the entire thing is modeled and analyzed in one step. You can get the response of the soil with the structure simultaneously, and there are two methods, numerical methods, to perform this type of analysis. Is FEM and FDM, and it is very good or very less complicated for geotech engineers, but it's a little too complex for structural engineers because it can be very difficult. The input of the information, the parameters that need to be included, it is a more detailed soil geotechnical methodology of performing the soil structure interaction. So we're gonna stick with the very simple one. So let's say that we have a pier. A lot of engineers tend to analyze a pier just by fixing where the foundation will be. Let's say it doesn't move in the X, Y, or Z, or it doesn't rotate. We analyze the entire structure assuming that it does not. This is probably not the best way of analyzing, since there is some type of flexibility when you consider the piles, or when you consider the pile caps or the entire foundation, which will influence the behavior of the entire structure. So let's say the peer reaction, it will depend absolutely on the soil and the foundation type that it is supported on. So in this case, we have the same peer, and we can obtain two different results from these particular peers, since one of them is considers the piles and the pile caps, and the other one does not. The force result on the deck and the pier depends on whether the foundation is flexible or not, or whether it is considered or not. So this is something that we have to take into consideration, even though trying to perform the simple method of doing the analysis is something that is acceptable, does not necessarily means that is the proper way of doing it. Let me just go over some of the modeling functions that we have available in the program, so that you can have an idea of how or which properties you can assign to the bridge to consider the soil interaction. We have some boundary conditions. I'll be going over the boundary conditions because these are very important when considering the soils, or when considering the whole foundation substructure portion of the bridge. In this case, we have multiple types of boundary conditions. We have nodal boundary conditions, element boundary conditions. In this case, we're gonna focus a little bit more on the nodal parts. We have the constraints, which is the supports part, in which we can constrain the degrees of freedom of a particular node, either translation or rotation. We also have elastic boundary conditions, which are the spring supports. We can do point spring supports, surface spring supports, general spring supports. We're gonna see some of the application of these properties into a model. We also have elastic link elements and general links, and these are for defining things such as bearings or isolators, dampers, and so on. The three main things that we're going to focus today are the spring supports specifically. In the program, we have point spring supports, in which you can define the stiffness in XYZ, or the rotational stiffness of the soil. You can get that information from the geotech. You can get the model subgrade reaction and just apply it directly into the model. We also have the surface spring support. So let's say you have a beam foundation, or you have a slab, a mat slab. You can assign the soil properties into the slab without having to going too much into detail for the geotech portion, just with the subgrade reaction, for example. And then we have the element boundary conditions, in when we can do the beam releases, in which we release the different degrees of freedom of an element. We can also do a rigid link, in which it connects rigidly two nodes. This is the boundary part for the elements, and these are some of the boundary conditions, such as the links. We have the elastic link for a bridge. Is basically the separation between, or the device that separates the superstructure from the substructure. We talked about it in the previous sessions, but then here you can define it: stiffness in X, Y, Z, translational and rotational. We also have the compression only elastic link. This is a lot of most of the times used for modeling the soil. But we also, as we know, soil cannot take any tension. We also have compression only properties for the links, and then we have the rigid. We also have the rigid link that connects two nodes with infinite stiffness, and we also have the multilinear one. So if you have, let's say, a PY curve, you can insert it here, and then you can use that for your soil properties. In the general link part, specifically, we have different types of devices that we can simulate in the program. We have dampers, isolators, compression only elements, tension only, plastic hinges, and soil springs. We can use linear, non-linear elements to do this type of to use these devices. We have for the element type the spring, dashpot, and spring and dashpot. And then for the force type, we have the viscoelastic damper, hysteretic system, seismic isolators. We have friction pendulum, triple friction pendulum, lead rubber bearing isolator. So these are things that you can just do for your information. Those are available in the program. Then we have the surface spring supports. These are used to define elastic supports on surfaces, represented by the modulus of spring. So you get the subgrade reactions from your soil. You get to talk to the geotech guy, and then from there you can obtain the program can distribute the soil springs throughout the entire surface. It can do two types. It can perform the convert to nodal spring, in which the spring supports are assigned to the nodes, or you can do the distributed spring, in which the spring is assigned to the entire element. It can be a plate, it can be a frame element. If you have, as I said, a mat foundation, a beam foundation, you can assign or distribute the soil properties throughout the entire element. Within the soil or functions that are available in the program, we also have something called integral bridge spring supports, which is a function that I'm gonna show you today, so that you can have an idea of how to apply those particular properties into an integral bridge. An integral bridge is one in which the deck and its supporting abutments and piers are integrated with our expansion joints to absorb the deformation of the bridge. It uses the flexibility of the abutment and piers to absorb that expansion. The main concern in these particular bridges is that the effect of the temperature variation on the deformation of the deck influences the entire behavior of the structure. This expansion and contraction of the bridge affects the backfill soil adjacent to the abutment, and also the compaction affects the behavior of the bridge. This back and forth between with those changes or variations of temperature have an entire effect of on the bridge, and also influences the behavior of the soil. So we have defined in the program, or we have generated a function in which the engineers can define the properties of the longitude, the length of the deck, the properties of the abutments, and then the program will calculate the spring properties throughout the entire abutment and will assign them automatically. This is the function in the program. It's called integral bridge spring supports, and what it does is that it applies the spring properties automatically in the program. You should just insert the soil properties, and then the springs are assigned automatically by the program. There are two types of springs when you use the abutment function, or the abutment spring, which is this one right here. One is the compression only to model the passive support by the backfill, and the other one is a footing, in which the supports are applied to the abutment in the direction of gravity. The other function that we have available is the pile spring, and here the soil properties are also applied automatically in the program, or by the program. You just have to insert the soil properties in it. What it does is it generates two types of springs. One that is the lateral restriction to model the lateral restraint of the soil in the piles, and the vertical springs that is to model the vertical stiffness adjacent to the piles. These are some of the properties that are required to define these type of spring supports. Uh, you have multiple types of soil. You have sand, clay, stiff clay, soft clay. Depending on the type of soil, you can see how the program calculates each behavior. If you, for example, want to see how the program is calculating the behavior of the sand, you can go into the online manual. You press F1 when you have the program open, and then you hit start, boundaries, and then you go to the spring supports function. Here we have the integral bridge spring support, and from here you can see a description of what the function is, the parameters that are required by the program, and then the computation of the stiffness for the abutments. You can have all the equations that the program uses to perform or to assign the soil properties. And then if you have, let's say, if you select some type of let's say sand, the program shows you the calculation that it uses in case of using, you know, sand or clay. When you use clay, the program also tells you which equations are using for the calculation of the spring stiffness for the clays. So just in case, you know, this is not a black box, the program is telling you how the program is calculating the entire stiffness of each one of the springs. In case that you want to use the automatic function, you can use this one, or you can talk to your geotech guy and ask him, you know, just give me to provide you the stiffness of each one of the springs for each layer or each location or each depth on your bridge, and then he'll be able to provide you with that information, and you can input it manually in the program. You can use it, you can input it through tables, you can input it through our graphical user interface, but then, you know, you have the automatic version in the program, so you might as well use it if your geotech guy agrees with it. So here are some of the parameters that the program uses for defining the spring properties, such as ground level, the C coordinates of the ground, the pile diameter, the unit weight of the soil, the earth pressure coefficient at rest, the coefficient of subgrade reaction, the internal friction angle, initial modulus. These are the things that the program uses to calculate the soil stiffness, and this is what you need to input in the program. So I'm gonna go over a model that we have, and that is also available for the users, in which we're going to apply the soil properties into the abutments and piles and see how the behavior of the soil influences the behavior of the bridge. So let me just go to the MIDAS Civil. And here we have our model. This is an skewed bridge with the integral portion, the abutments defined already in the program. For those of you who do not know how MIDASoft looks like, this is our graphical user interface. We have at the top the ribbon menu that is very similar to AutoCAD, Microsoft Office. We have generated this version of the program, or this part, just thinking about how our users can, it can be how easily to the users to utilize our program. We have in the ribbon menu, we have the different tabs, in which each one of the tabs indicates us the different functions that are available. So let's say for the load tab, you have the different types of loading: static, dynamic, moving load, temperature loading, construction stage loading. All of them are listed, and then from there you go from left to right to define the load cases and then apply the loading. This is how the workflow of the program is. Everything is from left to right, so you will not have any issues while modeling inside of it. We also have the tree menu, which is this part right here. In the tree menu we have something called tables, in which all the things that are assigned to the model are listed. You can generate a table for all the properties that are on in the model, and you can modify that table. For example, the nodes, you can modify the coordinates via Excel or just by inputting the nodes or location of each nodes right here. The same thing you have for all the parts of the structure. We also have the works tree, in which you can generate you can see the list of things that are assigned into the model. Here I use this a lot because I can see what our users input in their models, and for example, if you have an issue, we are the technical support guys that check your models and see what's happening to it, and from here I can see whatever you have added to the model, and I can check it. I can even check the properties that you have assigned and modifying them also from here. So it's a very useful function, which is the works tree. Then we have the groups. We have different groups assigned. This model has also construction stages, and we have different things here. Task pane. We have created a task pane function for you guys that is gonna list all the properties that are, or all the steps that are assigned into this model. So let's say I would like to locate an old task pane function that I had available. It's right here. Let me see right here. Let me use the user defined one that we have created, and then from here you can see the different functions that are available for you. These are the steps that you can use for defining the or assigning the properties. So let's say I would like to assign the spring supports. I hit on the spring supports, and the program is gonna redirect me to the integral bridge function through the task pane. We generated this task pane, so it will be easier for you to just click here, click on the spring supports, the supports, perform the analysis, and then verify the different results just from the task pane. So you have to go through the main menu. You can do this type of little program if you guys follow like different steps constantly. You can also do that in the program. Alright, and then you have the message window, in which the program communicates with you and tells you whether there is a problem with the model or not. And then we have the different views right here that we can change. In this case, what I'm gonna do is I'm gonna go to the boundary tab, and I'm gonna use the integral bridge function. You can also load it through the task pane, and then from here I'm gonna assign these spring supports into a group of supports. And then what I'm gonna do is I'm going to activate the second tree menu, and I'm just gonna activate the substructure. I can just right click on it and activate it, so I can only see that part. From here, what I'm gonna do is I'm going to change the units to keep inches, and then I'm gonna select from the element list function, I'm going to select the elements that I'm gonna assign into the abutments. So I can just click on this abutment part, and then from there I am going to select or delete the nodes that do not belong to this portion of the assignment. In this case, the program asks us for the node list. If you want to delete the nodes, just click here and erase them and press the enter button, and then from here, or the enter key, I'm sorry. From here, what I'm going to do is I'm going to select the nodes for the footing. The nodes for the footing are the nodes that are assigned at the bottom of the abutment, which are this one. Then from here, I'm going to define the height of the abutment, the width of the abutment, and the deck length. Obviously, these parameters are going to change as for the different projects. Then we have the specific gravity, the void ratio, and then from here let's apply the differential temperature of the deck, and then from here we will apply the foundation width and the bearing pressure. Here the alpha is gonna be using the properties of the material, and then from here what we'll do is we're gonna click apply, and the program is gonna do this one. It's going to apply spring support. Each one of the spring supports is generated via the or is shown using the hexagon. XYZ on the right, XYZ rotation on the left part, translation on the right part. So in this case we have X and Y translation, which are the horizontal degrees of freedom. So it's restraining it laterally, and then in this part we can see that it has X, Y, and Z. So the vertical portion is taken into consideration for this one, and also the rotation in the Y direction. We're going to do the same for the other abutment. In this case we're just gonna select it the same way, and then we're going to reselect the nodes. So let me just erase this, click enter or press the enter key, and then I'm going to select the nodes that are listed. Just unselect this one, and let me just reselect this one right here. Alright, perfect. After that, what I'm gonna do is I'm going to, we have the information of the abutment already defined, so let's just click apply. Let me see. Let me just check that the information was applied correctly. Let me just display all the spring supports. Alright, we have the spring supports on the left side. Let me just redo it on the right side. Alright. Let's select again the abutment, and let's select the nodes. Alright. And then here we go. We have the springs assigned to the abutment, and then what we're gonna do is we're gonna assign the the springs for the piles. In order for us to apply the springs on the piles, the first thing that we're going to do is we're gonna select the boundary functions, and we're going to go ahead and define the piles. Select the pile nodes. So we're gonna do something like this, in which we select the piles, and then we're gonna use the pile spring function, which is this one. From here we can tell the program the type of soil that we're using. In this case, let's use sand, the ground level, the diameters of the piles, so 18 inches in in this case. And then from there we can define the earth pressure, the subgrade reaction coefficient, and then we can simply just apply it. From here the program, what it's gonna do is it's gonna assign the spring supports in these directions. Also, in this case, what we're going to do is we're going to define the springs, the supports. On this model, they are defined right here. We're going to also define the supports at the bottom of the nodes of the piles. Just to have a vertical restriction, you can either do this or just use the vertical restriction that is generated from the piles. So let's define the supports and restraining it in the C direction. Or in this case, you can just restrain this portion of the wind and then just run the model with the soil springs vertical C direction. It's up to you. Let's just do it that way. Let me see if all the groups, you can check if all the tables belong, if all the springs properties, you can check them through the table, and you can also modify the properties through the table. And here I'm checking also that all of the spring supports belong to the group, because when I run this model now, they all will be activated in the construction stage in which they are assigned to be activated. So let me just run this one, and let's go back into the property. Alright, after we run this model, we're going to check the different results that are generated for assigning the spring properties. We can check the stresses on the plates for the abutments. We can also check the stresses in the piles due to the spring consideration, and also see how the entire behavior of the entire bridge is during the construction stages, and also after applying the different types of loads, such as the temperature, the moving load, dead load, live load, barrier loads. All the loads are considered, and then we can check how the behavior of the bridge is when we consider the entire spring supports. Right, so the program tells us, if there is anything wrong during the analysis, the program will tell us. And then from there we can check now the results of the functions. Let's see some of the reactions. So let's just run into the tags pane and let's check the reactions. We can see the reactions due to the self-weight. We can check the reaction on each one of the piles. Let me just reduce the scale of the arrows so that we can have a smaller one. We can also add the values here, so you can have an idea of what the each one of the reactions that are generated in the model. Also, for deformations, you can obtain the deformed shape of the bridge due to its self-weight. It's a very deformed way of showing it. You can also check the beam forces that are generated due to that particular load case. In this case, the self-weight. Let's check the reactions of the foundation. So here you can have an idea of what the values are for the reactions of the foundation. Let me just fix the figures on the legend, and let me change the properties of the legend. So if you change, let's say, to moment, and you change the units, the program automatically updates the units. So let's say keep inches, the program will change it to keep inches automatically. Okay. without any issue. Also, if you want to check the forces on the abutments, we have the plate forces and moments, and then from here let's check the forces due to the temperature gradient that are generated on the piles, on the abutments, I'm sorry. You can see here the moment generated in the abutments and the effect that the temperature has on the abutments directly. So this is a way of assigning soil springs for particular integral bridge or just for piles in the program. What I'm gonna do is I'm gonna jump into the other model that we have created, in which we're going to show you how to define how to define the piles in the model, and also how to define the slab in it. So what we're gonna do is we're gonna assign two foundations, two piles to each one of the columns or piers in this case, and also we're going to mesh the pile cap so that you can have an idea of how you can do it, and we're gonna use the surface spring so that you can see how you can assign it into the pile caps. So in this case, what I'm gonna do is I'm just gonna select these two nodes, I'm going to activate them, and then from the two nodes what I'm gonna do is I'm going to, let me just show them, to generate the location of the two piles for each column, and then I'm gonna show you how to mesh it. So in this case I'm gonna select the two nodes and I'm gonna use the translate function. I'm gonna translate these two nodes at an 2.2 meters to in the y direction, and also minus 2.2 in the other direction. Then from here what I'm gonna do is I'm going to rotate the nodes, in which I'm just gonna generate a circle that is gonna be what the pile will look like. In this case I'm gonna do it 10 times 360 degrees over 11, and about the z-axis, which will be the vertical direction in this node. And what I'm gonna do is what I'm gonna do is first I'm going to translate this node 0.75 meters in the x direction, and then this node that I just created, I'm gonna do the rotation of it. So it's gonna be 10 times 360 over 11, and then I'm gonna use this location as a reference to the translation. After I apply it, this is what is gonna be generated. I generated a circle with 1.5 meters diameter. So what I'm gonna do is I'm gonna select those new elements and also the node that I recently created, and I'm gonna translate it. So I'm gonna translate it from the center to this part, apply it, select it again, from the center to the other side of the bridge, and redo it for the other part. Perfect. From there, what I'm gonna do is I'm gonna select this node and I'm gonna translate it to generate the pile cap. So in this case, what it's gonna do is I'm gonna do 2 meters, 4 meters, and it's gonna assign it here. I'm gonna do the same node, but I'm just gonna do -4 to assign it on the opposite side, and then I'm gonna do -2 for the other side. Perfect. We have the entire location of the pile cap. The first thing that I'm gonna do is I'm gonna select the interior nodes, and I'm going to generate the piles for this particular model. So let me see if I have the section. I'm gonna create a section for the piles. So I go to the section properties, I add a new one, and this one is gonna have a 1.5 diameter. click OK, and then we have it defined. What I'm gonna do is I'm gonna extrude the element and generate the piles from those nodes. I use a extrude function. I'm gonna assign the pier section to it, and I am going to assign the pier material, I'm sorry, and the pile section to it. It's gonna be -1, and it's gonna be a 7-meter pile. If we apply it, we're gonna have something like this. These are the piles generated. Then from there, what I'm gonna do is I'm gonna mesh, or first translate these 4 nodes and then generate a mesh on each side of the bridge. So let me first translate these nodes, and we're gonna go from here to here, and then we're gonna use the auto mesh function, in which we can select either nodes, lines, line elements, or planar elements. In this case, we have nodes, so we're gonna select the area that we want to mesh. We can include or not the inner domain, which is the inner nodes, the interior nodes also, and then we can tell the program what the length or the size of the mesh is. So let's generate the material for the pier, and let's assign a thickness to it. We're gonna do a 2-meter pile cap, and then from there we can apply it, and this is generated right here. The same thing we can do for the other side of the bridge, in which we can select the 4 nodes, and then from there we can just apply it, and it's gonna be something like this. If we activate the entire bridge, we're gonna have something like this, in where we have the piles with its cap. So in this case, what I'm gonna do is I'm gonna select the plates, and I'm gonna show you how you can assign the spring supports into a plate. So let me show you the surface spring function. The surface spring converts the springs into nodal loads, or it's gonna assign it to the nodes, or you can also distribute it. So let's say if you have a beam in the foundation, you can tell the program what the width of the beam is, and the program is gonna distribute the load or the nodes into the beam. In this case, we have a plane, which is the pile caps. So in this case, we're gonna tell the program what the subgrade reaction is for that particular pier. So we have it there. Then if you see here, the program assigns the the pier caps, that it assigns the springs distributed throughout the entire cap. After that, we have the assignment of the spring supports. So let's assign the pile springs into those elements, and let's say for the piles that we recently generated, we're gonna assign the spring supports. We select them, these piles. We tell the program where the location of the ground is, the diameter of the pile, the subgrade reaction, and we hit apply. We have the location here. Same thing for the piles on the side of the bridge. Let's just rotate it here. And let's tell the program where the ground level is in this case. Perfect. After that, if you want to assign some type of restriction into the piles, or if you want to assign any other thing to the model, you can do it as well. Let me just check here the links. Not everything is fine. Here we have the links. Let me just assign it. Also, in this case, we have this model with links that are supporting the deck, In this case, what I'm gonna do is I'm gonna copy the links, these two nodes, and I'm gonna translate them, and I'm gonna tell the program to assign the properties or the node attributes to those particular nodes that I'm gonna translate. So here I have the devices that are supporting the deck. So what I'm gonna do is I'm gonna tell the program to translate, to copy these two devices into the other side of the bridge and copy the node attributes. You can copy the links that are assigned to the nodes or anything that is assigned to the nodes and intersect the frame. The same thing we're gonna do with the other side, because the right side of the columns do not have the spring supports in them. We apply them, and then after that we can check whether or not the springs have been assigned. So we had 6, now we have 8. Then we do a merge of the nodes, so to make sure that all the nodes are together, we do the merge, we select everything, and then from there we can run the model now. Let's just go back. Then from here we're gonna check the analysis results in the program and see what we can get from the spring supports assigned into the bridge. Alright, so let's see what the deformation will be due to the particular, let's say, dead load. Let's change the units 2 inches, and let's fix the legend to see what the behavior of the bridge will be. You can deform the bridge, and here we can see what the deformation will be due to the particular load case. If you have a moving load as well, since this model has the moving load, you can select the minimum and maximum moving load and see what the behavior of the bridge will be for that particular load case. You can also check the pile reactions or the forces on the piles, as I did in the previous model. You can check them here, and you can see, there's a significant amount of piles that is taken from this particular part. What we did in this case, we applied the nodes into the pile cap because we want the pile cap to consider the soil that is supported on. But if you don't want to, if you just want the piles to assume all the loading, you just simply disregard the pile cap and don't apply any spring supports to it. In this case, we have applied them to both of them, so we can also check the forces that are being generated on the pile caps. So I'm just gonna activate the pile cap on the right side, so that on the left side, I'm sorry, so that we can have an idea of what is happening in it. So let's say for the moving load, let's check what the behavior of the pile cap will be. We have concentration of loading on the the piles location, but then we also have different moments or shear forces that are assigned into the pile. So from these forces we can perform the design based on what the stresses that are generated on the piles. If you have an Excel sheet, you can perform the design of it through an Excel sheet, but the main thing is getting the force results, and this is what the program can do. If you want to check the results of, let's say, this element 182, you can get the forces using this box here, and you can tell the program which load case you want to check, and the program is gonna give you the forces that are being generated due to those particular load cases. You can export that to your Excel sheet, and then you can perform the design of these pile cap. After this, we're gonna see a little bit of, let's check, we're gonna see a little bit of the design as per Ashto. In the program, we have the Ashto LRFD available for design of the substructure. We can perform the design, we can get design outputs like this one. Graphically, the program can show us what the behavior of the structure will be with particular reinforcement, also the ratios, capacity over demand, and it will also generate a report in which all the equations that are being used, the program will explain them. Also the PM interaction curve in 3D, and we can use the design function as per Ashto to generate the design of the bridge. In this case, what we're gonna do is I'm gonna go over the design functions. You can select the Ashto LRFD under the design codes. You can apply the seismic provision as per Ashto, and then we have a function in the program in which you can also modify the strength reduction factors, you know, in the case that you need to or just want to check something. You can also modify the material for the design. So in this case, we have the ASTM available in the program, as well as the rebar information. You can modify it here. After that, we have the limiting of the rebar ratio as per Ashto as well, and we have the information for the design. So in the program, we have the column section for design, in which we can tell the program how much, or we can tell the program the covering thickness that we have, and the number of spirals that we have. In this case, we have P. I'm just gonna change it to the regular number of rebar. If you want to do that, go to Tools, Preferences, and do the Design and Load Case function. And here for material for rebar, you can select the ASTM, materials for DB, and then we can define it and select the rebar as per ASTM. So let's do the design first. We have the column section data for design, in which we can tell the program what the thickness is, and then we can also tell the program which rebars to use and the number. I replace. Then from there, the program can do the design of the piles from the load combinations. The first thing that you have to do before performing the design is generate the load combination under the concrete design tab. You can use the auto generation as per Ashto, and the program will generate them automatically. Then from there, you can perform the design for these piles. So after defining the design functions, you can do column design, and then from there the program is gonna take the load combinations and it's gonna perform the design of the piles. It's gonna tell us whether or not it complies with the codes, and it's gonna give us like an overall or general idea of the design of these piles. It's gonna provide us with the rebar information. It's gonna give us also the capacity, axial force, moment capacity, and also the interaction diagram. And as well, it's gonna provide us with the shear reinforcement, with the stirrups, the spacing of the stirrups. Here it's gonna give us the rebar information with those stirrups that we assigned to it. That's a way of doing it. If you want to check by member, you can also check by member individually. You can get a detailed report on each one of the equations that the program used for design, load combinations, information of the elements that you're designing, the moment, capacity, slenderness ratios, shear checks. You can also generate a PM curve for the design, as I mentioned, and you can also use a summary. You can generate a summary of the design that you just performed. That's one way of doing it. The other way of the other function that is available for design is the design check. So let's say we have the column section data for checking, and we have number 3 bars every, let's say, 10 inches or every 6 inches, and we tell the program that we have 12 rebars that are number 8 at 6 inches from the clear cover, 6 inches. If we want to add more, we can add more, and the program automatically updates the drawing. So from there we can tell the program, alright, so can you do the design check and see whether or not this reinforcement complies with the code. So the program now is doing the code check with the parameters that we just inserted, and it's gonna give us something like this, in which the program tells us, you know, the rebar information, the capacity of the that particular reinforcement, and also the shear capacity. And from there you can also generate the PM curve. You can also do the member design. You can generate the graphical part, the detail report, as I just did with the design, but this in this case is the check, so you can see what the program is checking in each one of the parameters in the ASHTO. Whether you want to save it or not, you can do it. Again, these are some of the functions that are available for the pile design, and with this particular session we were able to see what the program can do in terms of the definition of the soil spring supports. We also saw some of the functions that are available for piles, abutments, surface springs. That's basically most of the things that are available for applying the soil properties in the model. How easy it is to perform a more complete analysis, and also we saw some of the design functions that are available that you can all do them in the same platform, which is MIDAS Civil. Thank you all for your attention and for your time in attending this training. If you guys have any further questions, you can use our global technical support website, and here we provide the support to the entire world. So any questions that you have, you can just insert it into globalsupport.midasuser.com. Thank you very much for your attention. My name is Edgar de los Santos, and I hope you have a great rest of the day.